Definition and notation of a vector. Welcome, everyone. To begin our lesson today, let's take a moment to reflect on what we already know. In our previous studies of geometry and algebra, we have primarily dealt with quantities that can be described by just a single number. Think about things like the length of a line segment or the mass of an object. These are simple, one-dimensional descriptions. However, as we move into the realms of physics and advanced mathematics, you will find that these simple numerical descriptions are often insufficient to capture the full picture. There are many phenomena in the real world that we cannot fully explain with just a number. To accurately describe these complex situations, we need a more powerful concept, one that incorporates not just how much of something there is, but also in which direction that something is acting. This brings us to our main topic for today, the concept of a vector. Understanding the concept, scalar vs. vector. Now that we've introduced the idea that some quantities need more than just a single number to be described, we need to establish a clear distinction between two fundamental types of quantities, scalars and vectors. First, let's look at what we call a scalar quantity. A scalar is a quantity that is completely described by its magnitude alone, which is just a fancy way of saying it only needs a numerical value and a unit. Think about the examples you encounter every day: mass, temperature, time, or distance. For instance, if I tell you that a stone weighs 5 kilograms, you have all the information you need. There is no need to ask, 5 kilograms in which direction? The information is complete as it is. However, as we will dive into more deeply in the next slide, we encounter vector quantities. Unlike scalars, a vector requires both a magnitude and a specific direction to be fully described. Consider examples like velocity, force, acceleration, or displacement. If I simply tell you that a car is moving at 60 kilometers per hour, you might have a good idea of the speed, but the description is actually incomplete. To truly understand the car's motion, you need to know the direction, for example, 60 kilometers per hour towards the north. Understanding this difference between just a number and a number with a direction is the foundation for everything we are about to learn about vectors. Formal definition of a vector. Formally speaking, a vector is a mathematical quantity that possesses two essential characteristics. It has both a magnitude, which is its size or length, and a specific direction. You can't have one without the other and still call it a vector. To visualize this geometrically, the most fundamental example of a vector is what we call a directed line segment. Now you might be thinking, how is that different from a regular line segment we studied in basic geometry? Well, a standard line segment simply connects two points without any particular order. However, a directed line segment has a specific orientation. It features an arrowhead that tells us exactly which way we are pointing, indicating the path of movement from a starting point to an ending point. This distinction is crucial, as we will see in the next slide when we look at the specific notation used to represent these points. Now that we have established the difference between scalars and vectors in the previous slide, let's move into a more formal definition. Mathematical notation. Now that we understand the fundamental difference between scalars and vectors, let's move on to how we actually write these down in mathematics. To avoid any confusion between a simple number and a vector, we use specific notations. First, let's look at method A, which is what we call the directed segment notation. This is used when we can clearly see the start and end of the vector on a graph or a diagram. If we have a vector that starts at point A and moves towards point B, we write it as an A with an arrow pointing over to B. In this setup, point A is known as the initial point. Think of this as your starting line. Point B is called the terminal point, which is where the vector ends. It is crucial to remember that the arrow indicates the direction is strictly from A to B. Next, we have method B, which is the symbolic notation. Sometimes, we aren't looking at a specific diagram with labeled points, and we just want to talk about a vector in a general sense. In these cases, we use a lowercase letter with a small arrow placed directly over it, such as a with an arrow or V with an arrow. This notation allows us to focus purely on the magnitude and the direction of the vector, regardless of where it is positioned in space. As we will see in our next example involving displacement, being able to switch between these two notations will be very helpful. Real-world example, displacement. Now that we have covered the formal definitions and the notation, let's move away from abstract theory and look at a real-world example to see how a vector is actually constructed. We are going to look at the concept of displacement. Imagine a simple scenario. A person leaves their home, which we will label as point A, and walks to a grocery store, which we will label as point B. To turn this movement into a vector, let's break it down step by step. First, we need to identify the magnitude. In this case, the person walks a distance of 2 kilometers. This numerical value, 2 kilometers, represents our magnitude. It tells us how much distance was covered. Second, we must identify the direction. It isn't enough to just know the distance. We also need to know where they went. In our scenario, the grocery store is located exactly east of the home, so our direction is east. Third, we combine these two pieces of information. To have a complete description, we don't just say the person walked 2 kilometers, we say the displacement is 2 kilometers towards the east. By adding that direction, we have officially moved from a scalar quantity to a vector quantity. Finally, let's look at how we represent this mathematically, using the notation we discussed in the previous slide. If we use our points, the displacement vector is represented by an arrow pointing from A to B, which we write as A with an arrow over it to B. This shows the path starts at the initial point, A, and ends at the terminal point, B. Furthermore, if we want to assign this specific displacement to a variable, we can simply write it as D with an arrow over it. As we move to the next slide, keep this example in mind, because we will look at some common pitfalls where students often confuse these vector components with simple scalar values. Common mistakes to avoid. First, let's talk about the confusion between distance and displacement. This is a classic mistake. Remember our discussion on scalars versus vectors from earlier? Distance is a scalar. It only tells us how much ground was covered, like saying, I walked 5 kilometers. However, displacement is a vector. To make it a vector, you must include the direction, such as, I walked 5 kilometers north. Without that direction, you haven't fully described the displacement. Second, please be very careful not to ignore the arrowhead in your notation. When we write the notation for a vector with an arrow over A and B, it specifically means the movement starts at point A and ends at point B. It is crucial to understand that the vector AB is not the same as the vector BA. While they might have the same length, they are pointing in completely opposite directions. In the world of vectors, direction is everything. Finally, watch your notation closely when writing your answers. A very common error is writing a simple lowercase letter instead of writing with an arrow over it. In your textbooks and in my marking, a plain letter A usually refers only to the magnitude, the scalar size. But when you see A with that little arrow on top, that tells us we are talking about the full vector, including its direction. Now, before we wrap up our lesson with the final summary, I want to pause and highlight some common pitfalls. As you begin practicing these problems, you might encounter a few traps that even experienced students fall into. Keep these distinctions in mind, and you'll be well on your way to mastering this topic. Now, let's look at our key takeaways to solidify everything we've learned today. Key takeaways. First and foremost, remember that a vector is not just a number. Unlike the scalars we discussed earlier, a vector is a quantity that must be defined by both its magnitude, which is its size, and its direction. When we visualize this geometrically, we represent a vector as a directed line segment. As we saw in our earlier slides, this isn't just a simple line. It is a segment that possesses a specific orientation, indicated by an arrowhead. Now, let's quickly review the notation so you can recognize it in your future problems. If we are talking about a specific path from one point to another, We write a arrow B to represent a vector starting at point A and ending at point B. However, if we are referring to a vector more generally, without a specific starting point, we simply use a lowercase letter with an arrow over it, such as a vector or v vector. Finally, keep these two components distinct in your mind. Magnitude refers specifically to the length or the how much of the vector, while direction refers to its orientation or the where in space it is pointing. All right, we have reached the end of our lesson, so let's take a moment to recap the essential points we've covered today to ensure everything is clear. If you have mastered these fundamentals, you are well prepared to move on to more complex vector operations. Great job today!